This is the Chem 1 lecture over percent yield. So percent yield is a way to compare the amount actually obtained to the amount that was actually theoretically possible. So you're actually comparing how much was actually found during a lab versus how much was possible. So what you're doing is you're looking at the efficiency of a reaction. Obviously you want your percent yield to be close to 100. So this is used often in manufacturing processes where you want to make sure that however much you're getting in, you're getting out 100% of the possible product you could. You wouldn't want a 50% yield because that means somewhere along the way you're losing about half of what you should be getting. So a simple example of that is with our peanut butter and jelly example. So here we've got our equation here, right? 2 slices of bread, tablespoon of peanut butter, 3 teaspoons of jelly equals a sandwich. So if I started out with 12 slices of bread, how many sandwiches can I theoretically make? Well, that means I had 12 slices of bread, right? So for every 2 slices, I can make 1 sandwich. Okay, well that's pretty simple math. We're going to end up with 6 sandwiches. So that means theoretically in a perfect world, 12 slices of bread would give me 6 sandwiches. That is a theoretical yield. That's just looking at how much you started with and calculating how much you should have been able to make. But let's say I accidentally drop one of those pieces of bread on the floor. Okay, so now I only have 11, right? If I drop a slice of bread on the floor, I now can only make 5 sandwiches. So now we can look at the efficiency. I should have been able to make 6. I only made 5. So your percent yield equation is the actual yield. That's what's actually found in a lab versus a theoretical yield. So that's something that's calculated. So the actual yield, I was only able to make 5 sandwiches, but I calculated that I should have been able to make 6, multiply it by 100 to turn it into a percent, and you're going to get 83.33%. So I'm only 83% efficient in my sandwich making. So a couple things to keep in mind. Yield means product. So you can only put a number into that percent yield formula if it corresponds to a product. Product meaning the product side of the chemical equation. And the second thing, the units and the substance for the actual and the theoretical yield have to be the same. You're comparing the same thing, right? You're trying to find the efficiency of that reaction. So you have to compare, if it's grams of sodium chloride, then you have to compare it with grams of sodium chloride. You have to be sure you're comparing the same exact thing. So let's look at our first example. A chemist produced only 6.58 grams of compound, although her calculations indicated she should have produced 9. What was her percent yield? So remember, a quick way to write the formula, percent yield equals the actual over the theoretical times 100. So we're trying to find percent here. So we're given 2 numbers. It says that she produced only 6.58 grams. So is that something that she calculated or something that she actually found? That's something she actually found. So that's our actual yield. And then the second number, 9 grams, it says that she calculated that. So that's actually our theoretical yield. So to find our percent, we're going to take 6.58 grams, we don't know what the compound is, over 9.00 grams. Multiply it by 100, we're going to get our percent. You're going to get 73.11%. That is her percent yield. She's able to get about 73% of what she should have been able to get. Now the next problem is a little bit different. We're given a chemical reaction and we're told that we've got 75 grams of CO. So let's write that down underneath our chemical, 75 grams. And we were told that what was produced was 68.4 grams of CH3OH. We want to know the percent yield. So we're given 2 masses, and you might be tempted to go ahead and throw both of those into our percent formula, but the problem is, remember, in order to put it into our percent equation, it has to be a yield, it has to be a product, and CO is not a product, that's a reactant. So we cannot put that in there. The 68.4 is a yield, and it says that's how much was produced. So this is going to be our actual yield. I'm going to go ahead and label that with an A, but that 75 is not our theoretical. We can, though, use that to calculate how much should be theoretically made So using stoichiometry, we can calculate that. So that is going to become our theoretical. So we have to first calculate our theoretical using stoichiometry. So I'm going to start off with my 75 grams. And you might be wondering, what should we convert it to? Well, if our actual is CH3OH, that means that's what we're going to have to convert our theoretical yield into, because we have to be comparing the same thing. So the first thing we're going to have to do is take grams of CO and convert it to moles using the molar mass. So you add up together a carbon and an oxygen, you're going to get 28.01 grams of CO. Now that we have moles, we can use our mole ratio. Go back to that balanced equation. You can see that we have 1 CO for every 1 CH3OH, so that's a pretty simple mole ratio. Moles of CO goes on the bottom to cancel it out to 1 mole of CH3OH. Now we've converted to the correct substance. We need to convert it to grams since that's what our actual has, right? Our actual is grams of CH3OH, so I need to make sure that my theoretical, this one that I'm calculating, is the same. So we've got to take moles of CH3OH, cancel that guy out, and get the molar mass. So we have to add up a carbon, 4 hydrogens, and an oxygen. You're going to get 32.05 grams of CH3OH. So now we can do the math, multiply the top and bottom, and then divide, and you get your answer to be 85.8 grams. Now this right here is not our final answer, but this is our theoretical yield. It was when calculated using stoichiometry. So it's theoretically done, it wasn't actually done in a lab. It's saying, hey, if every single atom of our 75 grams of CO reacted exactly perfectly and nothing was lost, we would end up with 85.8 grams of CH3OH as a product. Now we can plug these guys into our percent formula. Remember, it's actual over theoretical times 100. So we've got to take our actual, 68.4 grams. And let's make sure we have the same substance, CH3OH, divided by that theoretical. We calculated that she should have gotten 85.8 grams. Now notice the substance is exactly the same, right? We're comparing the same thing. Multiply it by 100, and you're going to get 79.72% efficiency. Now this third problem, let's see, we were given an equation, it looks like it's balanced already. We're told that aluminum reacts with excess copper-2 sulfate. If 1.85 grams of aluminum, so we've got, let's go ahead and write that given out, 1.85 grams of aluminum. And the percent yield, so we're given the percent of copper, so we know this person is 56.60% efficient. We want to find out what the mass of copper was actually produced. So this is a little bit different. We want to find question mark grams of copper. We're given the percent. So in this problem, if you think about what we have and what we're trying to get to, if we're dealing with actual over theoretical times 100 equaling percent, when you think about what we've got, we've been given the percent, so we have this guy, and we're asked to find the actual, which means we're going to have to find the theoretical. Now remember, when you calculate it using stoichiometry. So what we're going to have to do is take that grams of aluminum, since that's not a yield, that can't go into our percent equation, we're going to have to convert it to a product. That's going to be our theoretical yield to find our actual. Now I chose to convert it to copper since that's the percent we have. If we'd been given percent of aluminum sulfate, I would have converted it to that. So first we've got to do that stoichiometry. So we've got to start with our 1.85 grams of aluminum. And we're going to have to convert it to grams of copper. So first things first, we've got to get it to moles. So the molar mass of aluminum, is 26.98 grams of aluminum for every 1 mole of aluminum. Now it's our mole ratio. Now this mole ratio, I have 2 moles of aluminum for 3 moles of copper. So I'm going to choose to put moles of aluminum on the bottom to cancel that out, to 3 moles of copper up top. Now it's a matter of canceling out the moles of copper to get it to grams. The molar mass of copper is 63.55 grams per mole. Multiply, so multiply across the top and the bottom, and then divide, and you get it to be 6.54 grams of copper. And since this is something that we have calculated, this is our theoretical yield. So now we can plug these values into our percent formula. Actual is what we're looking for. I'm just going to leave it in A. Theoretical, we have that, 6.54 grams of copper times 100 is going to equal 56.60%. Now at this point, it's an algebra problem. We need to solve for A. So what I suggest doing is first dividing both sides by 100 to moving it over, and then you end up with a proportion. So then you can cross multiply. If you cross multiply, you get A times 100 equals 6.54 grams times 56.6. Divide both sides by 100. So then you're going to get A, so you can crunch these numbers in. You're going to get A is 3.70 grams. So if they are only 56.6% efficient, that means they've only created 3.70 grams of copper. You could always check your work by making sure that you took the actual divided by that theoretical times 100 and make sure that you got 56.6%. There's a way to double check your work.